Hello everyone. Today let's discuss about the adaptive filtering. Let's try to understand what exactly adaptive filter is. Whatever the discussion that we had in the earlier classes with reference to the FAR filters designed using windowing technique or frequency sampling technique or IAR filters, all those filters are considered to be the fixed filters because the fact that the parameters of those filters do not change with respect to time. I mean to say the cutoff frequency or the bandwidth do not change with respect to time. Whereas in case of adaptive filters, these parameters may be bandwidth or not frequency or cutoff frequencies. These frequencies will change with respect to time. If these things have to change, it is necessary that the filter coefficients also need to change, which means that the filter coefficients that exist in the filter are functions of time, and hence we say that filters coefficients adopt themselves for the changes that would occur. The filter that we have fixed filters can be represented in the form of a block diagram that we see here. This is basically a fixed filter wherein the filter coefficients are constant, do not change with respect to time. You apply some input, you get some output. Whereas in case of adaptive filters, the filter coefficient, the fixed filters and adaptive filters will have similar kind of difference equation. The difference equation that we have represented here, y of n is equal to sigma I ranging from 0 to n a I of n x of n minus I minus j ranging sigma j ranging from 1 to m b j of n y of n minus j. If you look at this, ai and bj are the filter coefficients. X is basically the input and y happens to be the output. So this is basically the difference equation pertaining to an IAR system, because the fact that output is a function of previous output samples, that is y of n minus 1, y of n minus 2, etc. Thereby we can expect the filter to have poles, and hence we call this particular system to be an IAR filter. Whereas in case of fixed filters, you have the same equation except for the fact that ai and bj are not functions of time, which means that it is ai x of n minus I, bj y of n minus j. In case of adaptive filters, both these filter coefficients ai and bj are functions of n. But this equation can be converted into a difference equation of an FAR filter, which is basically a filter whose output is a function of present and previous input values, which means that the second term in this particular equation need to be 0. The second term need to be 0, which can happen only if bj of n happens to be 0. Y of n minus j cannot be 0 because it's the output. Therefore, only the filter coefficients need to be 0, which means that bj of n should be equal to 0 for j ranging from 1 to m to transform the equation that we have into an adaptive FAR filters. Let's discuss something about some matrix operations. Let's make an assumption that we have a vector of size d. We represent the x transpose wherein X happens to be a column vector, X transpose happens to be a row vector. And A is a matrix, it's a square matrix whose elements are A11, A12, A1D in the first row, A21, A22, A2D in the second row, and AD1, AD2 up to ADD in the dth row. The first subscript that we have here in all these elements or the components represent the number of the row in which the element is present. The second number that we have simply represents the element value. So it's A11, A12 is the first element of the first row, second element of the first row, etc. If you perform X transpose A transpose A into X, this is basically the matrix multiplication. If you perform this multiplication, you get a scalar quantity. So you can perform the gradient operation, which is nothing but the derivative. The symbol that we have here is del of the scalar quantity Q, which is nothing but X transpose AX, can be written as 2A X transpose. And of course, the differentiation of the derivative is performed with reference to the elements of the matrix A. That's what the subscript A in the gradient symbol represents. So for the purpose of illustration, let's assume D as 2. Therefore, X transpose turns out to be X1, X2. A represents A11, A12, A21, A22. So like in this multiplication, let me perform A into X. So this is A. X is nothing but the transpose of X transpose, and hence it's a column vector. And if you perform the multiplication, this is what you get. Hope all of you are familiar with the matrix multiplication. The vector matrix A is basically a 2 by 2 matrix. Vector X happens to be 2 by 1 matrix, 1 by 2 by 1 matrix. Therefore, the product that we have will be 2 by 1 matrix. If you look at this, A11, there's the first element of this multiplied by x1 plus A12 into x2 happens to be the first element, and the second one happens to be A21 into x1, A22 into x2. So this turns out to be second matrix. It is a 2 row and 1 column matrix that we have, which means that it's a column vector. The second product that we have is X transpose A transpose. X transpose is x1, x2. A transpose is nothing but columns being changed to rows and rows being changed to columns. Thereby, A transpose is nothing but A11, A21 and A12, A22. X transpose is 1 by 2 size and A transpose is of 2 by 2 size, and hence if you perform the multiplication, what you have is nothing but 1 by 2 size, which is indicated here. Therefore, you have a 1 row and 2 elements. The elements that we have here are x1, a1, a11 plus x2, a12 being the first element. Second element is x1, a21 plus x2, a22. This is the second element. So if you perform the multiplication of these two, that is X transpose A transpose, which happens to be 1 by 2 matrix, and AX, which happens to be 2 by 1 matrix. I have written the matrix is here. This is X transpose A transpose, and this is AX. So this is basically X transpose A transpose is 1 by 2 matrix. AX is a 2 by 1 matrix, and hence the product of these two happens to be 1 by 1. So which is nothing but A11 x1 plus A12 x2 whole square plus A21 x1 plus A22 x2 whole square. So this is basically a single value and hence it's a scalar quantity. So we represent this scalar quantity as q. Let's perform the gradient operation on the scalar quantity q with reference to the elements of the matrix A. So del A of q is basically a matrix of this kind. Partial derivative of q with reference to A11, partial derivative of q with reference to A12, similarly with reference to A21 and A22. So if you look here, we have performed the derivative of this scalar quantity with reference to different elements of the matrix that we have here. So the first one is nothing but it's a derivative of this particular value. This q is nothing but this. So it is, if you look at the second term, does not contain a11 and hence derivative of this second term is 0. Derivative of the first term is 2 into this multiplied plus 2 into this multiplied by derivative of this, which means that it is 2 into a11 x1 plus a12 x2 multiplied by derivative of a11 x1 plus a12 x2. This derivative of the second term here is 0 and then derivative of this with reference to a11 is x1. So this is what we have. So this is nothing but 2x1 a11 x1 plus a12 x2. Similarly, the second term in the first row, derivative partial derivative of q with respect to a12 is again the derivative of this, in which case the first term is 0. Sorry, yes, first term is 0 because it is to be precise, the second term, because the fact that this term is independent of a12 and hence the derivative of this is 0. The derivative of this is 2 into the whole thing multiplied with derivative of this term. So it is 2 into x2 a11 x1 plus a2. Similarly, other two derivatives that we have here will provide us these values. So we have the elements of the gradient of the scalar quantity with reference to the coefficients of or the elements of the matrix A being this. These are nothing but the values that we have calculated here. So 2 is common, so I can take it outside. So this is what we have. This matrix can be written as A11, A12, A21, A22 multiplied by x1 square, x1, x2 and x1, x2, x2 square. We can put it this way. If you perform the multiplication of this, this is what you get. This is a 2 by 2 matrix. Even here this is 2 by 2 and this is also 2 by 2 and the product also be 2 by 2. Now this x1 square, x1, x2, x1, x2, x2 square can be written in this particular form. That is x1, x2, which is nothing but a vector x multiplied by x transpose, that is x1, x2. If we perform the multiplication, if you look at this, this is a column vector, it is 2 by 1 matrix, and this is nothing but a row vector, and hence the product of these two turn out to be 2 by 2. 2 by 1 and this is 1 by 2, so the product is 2 by 2. So is x1, x1, x square, x1, x2, x1, x2 and x2 into x2, x2 square. So the first matrix or the vector is nothing but x and the second vector is x transpose. Therefore, this whole thing can be written as 2 into a into x, x transpose. So these are some matrix identities that can be used for the purpose of simplification. If you look at the first equation which we proved, if you want to get this, it is necessary that you have to perform a into x, x transpose into a transpose. So you have two multiplication and again multiplication of these two, which is nothing but the second multiplication, a third multiplication rather, and then you have to perform the differentiation. So you have a lot of calculations being involved in this operation. To overcome this particular problem, I can simply perform this, which means that x transpose is the one that we perform is one multiplication and A is another multiplication. Therefore, the number of multiplications and the calculations can considerably be used by using these matrix identities. So these are the concepts normally that we use in rest of the discussions that we are going to have.